light, one of the first things in our universe, and it's kind of ironic, it's the thing that we still find hard to understand. It puzzled physicists for many years. Now, Newton had an understanding of light. He talked about little corpuscles of light. So he imagined light as little particles streaming through space. Now, the nice thing about a particle model is it explains how light gets from the sun to the earth through the empty void of space, because a particle doesn't need anything. In fact, nothing being there makes it easier for the particles to get to the earth. Other people have a thought that light was a wave. Now, I'm sure you've seen this before. It's the standard model of a wave. It looks like something's moving across the screen horizontally here, but actually what's happening is that the particles of the medium are moving up and down, and there's an apparent movement of a wave across there. A wave can transfer energy from one place to another, but there's no particles, except that a wave needs a medium for it to mean anything. So is light a particle, is it a wave? Well, one of the definitive experiments to answer that question for good was Young's double-slit experiment. Now, Young's experiment was fairly simple. He had a light source, he had a barrier with two little slits in it, and he had a screen on which the light was going to fall. Now, if light's a particle, what would we expect to see forming on the screen? Well, we would imagine that particles that can travel through the gaps in the screen would travel through the gaps, and so particles of light would be travelling through these two gaps here. But of course, particles that don't hit the gaps are going to be stopped by the barrier. So what we're going to end up with is two regions on the screen here where we're going to see areas of brightness. And those regions of brightness, two of them are just going to match the two slits. There'll be nothing in the middle and those two bright regions. What about if light, instead of being a particle, what about if light was a wave? Well, let's imagine that we've got our two waves. I'm just going to colour them green and blue just for convenience. They're not actually green and blue, of course. They're both the same light coming from the same light source, arriving at those two gaps. Well, actually, unlike particles, in the central part of the screen, we'd see those two waves have got an equal distance to travel. So the two waves would arrive at the screen at this point in time in phase with each other. Now, what we know is that when we've got two waves in phase, they're going to superimpose, and we're going to get a wave that's actually going to be twice the amplitude at that point. So contrary to the particle model, we'd actually predict a central bright spot there on the screen where the two light waves arrive in phase. What happens if we consider a little bit off to the side there? Well, you can see that the green light ray now has a further distance to travel. So the blue will arrive at that point in the on the screen, and the green one, the green one will arrive a little bit behind it. Well, there'll be a point on the screen where it arrives 180 degrees out of phase. They will superimpose and cancel out. In other words, there'll be a dark spot on the screen. If we exaggerate that a little bit further and imagine a further distance for our green light ray to travel, now maybe our green light wave has a whole wavelength of extra distance to travel, which means it'll arrive in phase again. So now we're going to see a bright spot. And as we keep increasing the angle, we're going to see regions of darkness and brightness. We're going to see a pattern on the screen that's very, very different from the particle model. And the pattern on the screen that we get with a wave model is exactly the results that Young got. I'll show you with a laser. So here I've got a laser light and I'm putting in front of it an optical thing just like Young's double slits. And you can see when the slits are in front of it, we get a multiple pattern of light. So we make the slits closer together, then the areas between the brightness and the darkness are wider angles, just as we'd expect. So that pretty much shows us that light is behaving like a wave. So Young's double slit experiment shows us pretty conclusively that light is a wave because of the patterns that we got on the screen of lightness and dark and light and dark as the two light waves from each slit interfere with each other either constructively, making a bright spot, or destructively. Now, interference is a property of waves. Two waves can superimpose, be in the same place at the same time. Two particles can't be, they collide and smash. So that was pretty convincing that light is a wave. Now, if light's a wave, it has to have a medium to travel upon. Otherwise, in what sense is it a wave? What's a wave without the medium? What's waving if you don't have a medium? So, even though scientists hadn't measured the medium for light, hadn't been able to detect the medium for light, they hypothesized that this must exist, and they gave it the name, the luminiferous ether. Now, hypothesizing things that we can't directly measure is not unusual. We hypothesize electrons even long before we could directly measure them. So it's not such a weird idea after all, given the evidence was there that light is in fact a wave because of Young's experiment. So, what properties would this ether have? Well, first of all, it has to fill all of space, including the vacuum of space. It has to fill the atmosphere. It has to fill objects like glass that light can travel through. So it has to fill everything. It also has to be very elastic because not much energy is lost. The light gets from the sun to the earth, not losing much energy along the way. It also has to have this weird property that it can transmit the light waves very fast. Well, we know with sound waves, for example, they travel more quickly in more rigid objects. So it's kind of this very rigid but elastic, and yet the planets can move through it without there being any drag. So it had a few weird kind of properties. Nevertheless, the name that we gave it was the luminiferous ether, which was the medium on which light travels.